Hello everyone and welcome. I am Max Naars from ISWA and I am introducing you to today's webinar on the impact of management choices on landfill methane emissions. Thank you for connecting with us from around the world. In a moment we will introduce you to the speakers of this webinar, but first a brief practical note. At the end of the last presentation, so the last of all the presentations, there will be a questions and answer session. However, the speakers also will be able to answer questions in the questions bar during the other presentations. All participants are encouraged to type questions in the questions window you can find to your right. Before we dive in, I would like to thank our sponsors and Platinum members. The work we are doing would not be possible without their contributions. Hence, I would like to thank our sponsors Veolia, the City of Rotterdam, Ecomondo, and IFAD. They are our main sponsors, and we are grateful for their support. Thanks also goes out to our Platinum members. Without the generosity of our sponsors and Platinum members, it would be hard to do what we do. I would also like to take a brief moment to introduce several of you joining today are not yet members. The International Solid Waste Association, ISWA, is a global, independent, and non-profit making association, working in the public interest, and is the only worldwide association promoting comprehensive and professional waste management and the transition to the circular economy. We are open to individuals and organizations, members from the scientific community, public institutions, and public and private companies from all over the world, working in the field of waste management or interested in waste management. ISWA is the only worldwide waste association that enables its members to network with professionals, companies, and institutional representatives. ISWA's mission is to promote and to develop sustainable and professional waste management worldwide. We have members from over 100 countries, which you can see briefly in this world map. If you're not yet a member, please take a brief moment to visit our membership page via the link on the screen. We have flexible membership options with discounts for students, low-income countries, and online members. Without further ado, I would like to introduce the speakers of today, who will be joining us from all over the world. Speaking today are James Law, Hayo Sharf, Jonathan Shamrock, Soon Hong Yang, Sam Taremba, Dennis Segers, Tiago Villas-Boas-Sanon, and Bob Dick. Over to our first speaker, Mr. James Law, Vice President of SCS Engineers, Chair of the ISWA Working Group on Landfill, and Chair of the ISWA Task Force on Closing Dump Sites. Over to you, James.
Thank you, Max. Good morning and good afternoon and good evening to everybody from all over the world participating in this incredible webinars that the ISWA Working Group on Landfill has put together for sharing information as well as for education purpose. The working group has a mission to promote best waste management practice around the world, and as well as a transition to a circular economy. Today we have a group of excellent waste management professionals and experts who have volunteered their free time for the last 6 to 8 months to analyze various scenarios and results to be presented in this today's webinar. First, allow me to introduce Hayo Sharf, who proposed this initiative and managed this best team ever for the task of exploring scenarios and as well as the impact of landfill management choices on landfill methane emissions in 6 different continents and with different climate zones. Hayo is a research and development manager at NV Vazo Holdings in Netherlands. He is a longtime member of this working group and has 30+ years of experience in the waste management industries. He's the chairman of the Landfill Policy Working Group of the Dutch Waste Management Associations and the vice chairman of the Landfill Committees of the European Federations of Waste Management and Environmental Services, as well as he's the chairman of the European Commission's Working Group for the EU guidance document on landfill gas control. With this, let's welcome Hale to introduce today's landfill gas emission topics that relates to climate change. Hale, floor is yours.
Thank you very much, James. Welcome everybody from all over the world. I will start with a brief introduction of this initiative, why we want to do this and what our goal is. Our goal is to compile facts and arguments in a white paper in which the ISWA Working Group on Landfill clarifies to both regulators and operators which realistic management choices during landfill operation provide the best options to minimize greenhouse gas emissions from landfills and over their entire lifetime. Now, why did that come up? Because in landfill gas assessments, usually a generic landfill gas recovery efficiency is used for calculation purposes. But we all know that during the lifetime of a landfill, there are a lot of changes that affect the landfill gas recovery efficiency. And the impact of these management choices on methane emissions during the landfill life is very poorly described in literature. So in our opinion, there's a knowledge gap, and it is our intention to bridge this knowledge gap with the experience of the members of the ISWA Working Group on Landfill. And we will try to illustrate the impact of different management choices. So you probably all know where landfill gas comes from. It's decay of organic matter inside the waste body by microbes. And we will focus on landfill gas and more in particular on methane in the landfill gas. We will follow IPCC recommendations as much as possible because they are basically the highest authority on how you have to calculate landfill gas generation and consequently emission. IPCC so far has considered the amount of nitrous oxide in landfill gas negligible. But there are landfills where the concentrations of CFCs, and they have an incredibly high global warming potential, is so high that they can contribute up to 10% of the landfill's greenhouse gas emissions. This situation only is rare, and that cannot be, so it depends on the individual landfill, and it cannot be considered in a generic modeling approach. More recently, information has become available on carbon black, basically soot, as a greenhouse gas. Carbon black is relevant for landfills as it emits from landfill fires, but ISWA discourages landfill fires, and therefore we have also decided to exclude carbon black from our approach. Secretly, there's another reason, because there is no quantitative information available on carbon black yet, so even if we wanted to, we couldn't possibly start calculating it. A literature review would have been the first thing to consider, but that is a real challenge because operational conditions in literature are usually poorly described, and that makes a comparison very difficult. So therefore, we decided to design plausible scenarios, operational scenarios for each continent, and then illustrate the greenhouse gas impacts of these realistic management choices for these continents by means of modeling. We focused on large relatively large landfills, as they normally service an urban environment, and several UN bodies estimate that by 2050, 70% of the world population will actually live in an urban environment. So that means that the main global warming impact will come from large urban landfills and not so much from rural situations. We will focus on comparing typical scenarios for each continent, but not necessarily all scenarios imaginable. That would be an enormous calculating effort, and the aim is to illustrate. I would also like to stress that we used a single phase model. That means that for all parameters, we had to calculate weighted averages with IPCC default values. We cannot show all those calculations in this presentation, in this webinar, but at some point we will produce a repository where all the modeling, all the individual modeling exercises can be downloaded and checked, so you can also check all the different parameters and how they were derived. For reasons of comparability between the continents, we have chosen to model a waste input of 500,000 metric tons per year. And apart from the annual waste input, a scenario also consists of a number of years that specific amount is landfilled, the typical waste composition, the climatic conditions, and the level of gas control. So this is basically our dashboard. On the left, you see the operational aspects, the 500,000 tons per year. The operational period, that is in most scenarios 30 years, but in a few exemptions it is 40 years. The waste composition, and then in the middle you see three columns that are blue, and they basically represent all the IPCC recommended default values. So IPCC distinguishes between 4 climate types, and they have specific categories for how landfills are managed. We, in general, have chosen the well-managed anaerobic landfills, since we will focus at large urban landfill sites that, in general, have an organization managing them that is capable of managing a sanitary landfill, so well managed. There are a few exceptions. Now that results into parameters, but the parameters, the 3 top parameters that are listed here, DOC, that is the degradable organic carbon in the waste, the fraction of degradable organic carbon in the waste, the DOCF, that is the fraction of that degradable organic carbon that actually does degrade under landfill conditions, and the reaction rate constant. They have been calculated with the default, the recommended values for each individual waste component. So that is different in each scenario because it's a weighted average of the IPCC recommendations. And then on the right, you see gas control measures. I will get back to that later. I will first explain what we did with the waste input. Because landfill operators, they can make management choices such as cell size, when to install wells, when to start recovery, how to control recovery, when to put or not put in a surface sealing, when to end active recovery, what kind of passive treatment to realize, etc. Now, that gives you an enormous amount of different combinations, and we decided to reduce the amount of combinations to 4. That there is no gas control, which of course results in 0% gas recovery, control after operation of the landfill. So in most cases that starts in year 32, and then there can be 50 to 90% gas recovery depending on the type of cover. Then control cell by cell. And we decided to assume that the cell is operated for 3 years. So in year 4, you can start extracting gas from that particular cell, again with 50 to 90% recovery. And the last one is control during filling. And we decided that during filling, you already install your gas extraction system, either with vertical wells that you raise or with horizontal wells that you put in each different layer of waste. You already start after 1 year. And in the first years, because of technical reasons, you will probably have a relatively low gas recovery rate, but at least you start early. And then in addition, the gas recovery percentage can be raised because, for instance, it is assumed that at some point a surface sealing is installed, or that over-extraction is applied, or that improved oxidation measures have been taken. IPCC gives for oxidation in the cover layer a default value of 10%. These are all options that the operator can decide on. Lowering the degradable organic carbon input also influences the methane generation. But this is a waste management choice that is normally not made by the operator, but by the state or a regulatory agency. And the aim here is landfill diversion. So we decided to accommodate this, even though we are looking at individual landfills, by taking out an amount of waste. So you are mimicking the landfill diversion. So for instance, if you take out 100,000 tons of food waste, then the total input goes down, but also the waste composition goes down, because that means that the food waste percentage is lowered. But since the same absolute amount of paper, wood and industrial waste and non-degradables are put in, that percentage increases. Hey, have we lost the presentation? I suddenly see myself. Okay, here we are again. So much for an introduction. We have prepared scenarios for each continent and waste management options that we consider relevant for those continents. And today we will present the modeling results from these scenarios. And the intention of this webinar is to make use of your experience and solicit your comments. So if you have any comments, please share them with us in the Q&A site, or send an email, or however you would like to do it. We will then compile the comments and recommendations, and we will then decide what we want to clarify and or amend. And after the webinar, we will then fine-tune the scenarios and the results, and the results will be published in an ISWA White Paper, for which we will probably need some time. So don't expect to receive that tomorrow. With that, I would like to hand you over to Jonathan Shamrock, who will inform you about management choices in Oceania. And Jonathan is a solid waste engineer with over 25 years experience in landfill development issues, including design and construction supervision of landfill gas extraction, and not only in New Zealand and Australia, but also on Fiji, Africa in general, and South Africa in particular. Jonathan is also the chairman of the International Geosynthetic Society Technical Committee on Barriers and vice president of the Australasian chapter of the International Geosynthetics Society. So please, Jonathan, the floor is yours.
Thanks, hey Joe, and And hello from Friday. It's just gone after 12 o'clock here, so I'm speaking to you from tomorrow. So just brief rundown of the current situation in Australia and New Zealand. Again, we were focusing on large metropolitan areas that have engineered landfills generally operated to sanitary landfill standards. In both countries at the moment, there's no nationally legislated diversion of organics from landfill yet, but these are being recommended. In New Zealand, there's the Climate Change Commission report, which was published in May 2021, and that has advised that that organic waste to landfill should be reduced by 50% by 2035. And in Australia, there's the National Waste Policy Action Plan, published in 2019, and that advises a 50% diversion of organics from landfill by 2030. So I think both countries have that as a target. The landfills are generally in large metropolitan areas, and they have landfill gas extraction systems to flare and to power generation. In New Zealand, early extraction of landfill gas is legislated. So if a site is going to be larger than 1 million tonnes, it must, after it has greater than 200,000 tonnes in place, install a gas extraction system and either send that to flare or to power. This is typically achieved through vertical extendable gas wells. In Australia, there's no fixed guidance on when the landfill gas system is to be installed, but there are limits on things like methane at the site's boundary or surface emissions that typically drive when landfill gas systems are installed. And this is typically done through early collection using sacrificial horizontal wells, typically to manage odor. So looking at the major climatic areas that we did look at in the major cities are typically on the eastern coast of Australia and New Zealand, and those both fall in a very similar climate zone, so temperate wet. The climate change emission factors that we used and the greenhouse gas, as Heijo described. In New Zealand, there's an additional requirement that there's a unique emissions factor calculation that's done for each site, and that the liabilities for any landfill or organic waste that's landfilled is calculated per ton of waste that goes into the site. So there's a incentive to keep track of what organic waste are going into the landfill. And the Australian input parameters are as per the National Greenhouse Gas and Energy Reporting Determination. So our baseline New Zealand scenario would be, as Heijo described, 500,000 tonnes per year, 30-year period with a typical New Zealand waste composition, temperate wet, and the derived DOC, DOCF, and K factors from that. But the baseline scenario in New Zealand was gas control during the cell operation, so extracting gas almost straight away. And our second scenario for New Zealand would be reducing the organics by 50%. That obviously reduces the waste tonnage inputs, adjusts the DOC, DOCF, and K. In Australia, we took the baseline scenario as the 500,000 tonnes a year at a typical Australian composition, but the baseline scenario was assumed to be that control after the landfill has ceased filling, so right at the end of its operational life. So that's typically a worst case scenario. And the second scenario we looked at for Australia was in what impact would early extraction have in that. So exactly the same input parameters, but looking at control of the extraction during the site's operational life. And then the last scenario we looked at for Australia was still doing early extraction, but then on top of that, adding a reduction of 50% of the organic waste to the scenario. So that essentially leads to these three curves, and we'll start off with the New Zealand baseline curve, which is the green line. And you can see that reduces to the orange line for the reduced organics. And with the reduced organics, if we reduce our organics by 50%, the amount of methane emitted with early extraction for both scenarios is roughly 30%. You can see the massive difference of no early gas extraction, which is the Australian base case, which is the grey line, and the dramatic impact that early extraction has. It drops the grey line to the yellow line, so that yellow line is only 40% of where the grey line was. And then the last scenario is if we do early gas extraction and reduction of organics in Australia, we're down to roughly 10% of what the baseline value was. So I think that just illustrates that you get massive gains by extracting the gas early, so installing extraction as you go along, and then obviously by reducing the organics, you're also going to bring down the amount of methane that's emitted from landfills. So I'd like to pass over to Mr. Soon Hoon Yang from Eco Ideal Consulting to cover the Asia representative. Soon has a Master of Science from Lund University, Sweden, and an environmental degree from Massey University in New Zealand. He has vast experience in policy and strategies, waste minimization, recycling, recovery, and safe disposal, landfill gas power generation projects throughout Malaysia, Singapore, Indonesia, and Uzbekistan. Soon, the floor is yours.
Thank you very much, Jonathan. Greetings from Malaysia, everyone. I hope everyone is staying safe under the COVID. So I'm happy to be with you today, introducing my research with my team on the Asia scenario. So, well, Asia covers a lot of different climatic zones, as you imagine, but what we have done is we have focused mainly on the tropical wet situation. And in terms of the landfill operational aspects, we are taking the same as previous speaker has took 500,000 tons per year. And of course, in Asia, across Asia, I think there's still a lot of open dumps and all that going on. But as mentioned by Heyo earlier, the well-managed anaerobic landfills are becoming the mainstream disposal options now. So that's our baseline for Asia. For a typical waste composition in Asia, of course, it doesn't represent the whole Asia, but this is the case for Malaysia, at least, as an example. We Asians love food, yeah? We eat a lot of food and, of course, throw away a lot of food waste. So just taking the food waste out as a stream is almost 40% of the waste that's being dumped into the landfill today. So it's a major portion of the methane sources coming out. So for Asia, we have looked at 3 management options. The first one, similar to what Jonathan has presented, is diverting the food waste as an option, converting them to energy or compost. Second one is the early extraction, meaning we install the extraction pipes not after the cell is finished, but during the operation. And finally, the HDPE liner as the final cover to trap the gas in a better manner. I'll go one by one. First, we start with the food waste. So unlike what Jonathan has presented, 50%, I think we have a smaller ambition, 20% diversion of food waste. This is taken from master plan study in Malaysia for food waste diversion. So this is the basis for our modeling. So for this scenario, if you look at the left side is the baseline emission pattern over 30 years. And on the right side is the after the diversion scenario. So you'll see there will be a decrease in the methane emissions of around 11% in our case. So this is to be expected, but 20% will give you about 11% of methane reduction from landfill. Next one is on the early extraction, as I mentioned. As you can see here, the example of how horizontal pipes are installed while the landfill is being operated. And this has been done physically, and I have been involved in projects like this. And here are the results. Again, on the left, I have the baseline scenario, and on the right, I have the one with the management options applied. So you will see here that in general, what happened is the recovery rate increases as expected because you are extracting earlier. And our total is about 16% more if you don't do early extraction. And overall reduction of the emission from the landfill will be reduced by 11%. So this is also a good result if you do this. Obviously, the early extraction will very much depends on your design of the landfill cell and how you operate, but we have seen that it's been possible and definitely beneficial for methane reduction. The final one is on this final cover. In this case, we are simulating HDPE final cover on top of the swell cover. Here, again, I think I'll go straight into the results for my case. On the left, again, is the baseline, and on the right is the outcome from the management options. Because of the HDPE liner, you see that there's a huge increase in the collection efficiency, estimated to be up to 90% of the model estimation. So naturally, you imagine that the recovery rate for the landfill gas will be much higher, and in terms of total emission from the landfill gas, from the landfill will be reduced. So you see a significant impact on the reduction here on this case. So those are the three scenarios that my team has modeled and presented. And I think I'll pass on now to the next continent, which is Africa. So let me quickly introduce the two speakers for Africa. The first one being Mr. Sam Tarmoa. Sam is the founder and executive director of Uganda Waste Management and Administration Confederation. He's very much involved in strengthening capacity of a local council in solid waste related matter. And second speaker will be Dennis Ziggers. Dennis has been working 20 years as an international project manager in solid waste management project in designing and construction of different types of landfill and landfill gas projects. And he works for a Dutch company called Tritech Nature. Over to you, Sam.
Thank you so much, Sun. I send you all greetings from Kampala, capital Uganda, and welcome you all to be part and parcel of this webinar. Regarding the African continent, I will be using concurrently dump sites and landfills, because as we all know, the characteristics of uncontrolled dumping of waste, urban areas with large scale on dump sites, insufficient or absent of landfill gas extraction or treatment, and even no separation of organics prior to dumping of wastes still exists in so many African countries at large. When this came up, together with the expertise of all international and local experts, we tried to bring this closer to what can be done. And allow me now briefly take you through the trend as it is in Africa, where due to urbanization and population growth in the last decade, there is a significant increase in waste generation overall. And this is especially in low and middle income countries where waste collection and treatment rate is still below average. The outcome from this poor management of waste is twofold, where we find ourselves in situations of floods, air pollution, and spread of disease vectors due to uncontrolled waste. And on the other hand, dumping on less managed dump sites or landfills, resulting in considerable methane emissions. In Africa, there has been and still there is limited strategies and control of landfill gas emissions. Now, this is as a result of many factors, and if I may pick a few, it ranges from lack of expertise, inadequate knowledge of the technology involved, lack of political will, inadequate funding for landfill gas utilization projects, and monopoly of power sector, among others. Now, with much focus on globalization and to a very big extent with African continent starting to engage and give much more needed focus to environment and management, it is very key and timely to engage with the world on sustainable growth. We went out and connected with so many expertise, among others who is Dennis. With your permission, you will allow me call him on board to demonstrate to us different scenarios by using selected models to measure the impact of landfill management choices on methane, which we are looking forward to help strengthen the capacities in Africa regarding landfill gas emissions control. Dennis, please.
Thank you, Sam. Thank you for the introduction of the African continent and the landfill situation over there. I jump to the next sheet and introduce to you the two basic scenarios we defined for the African continent. Of course, you can go as far as you want with detailization of scenarios, but just to drop down to the headlines that Hayo already defined, we came up with a Northern African desert kind of climate scenario and a more subtropical wet climatological scenario. And for those two base scenarios, we have defined two management options to elaborate. And as Sam already introduced, the level of legislation, enforcement, and political will is still lagging behind in most of the African countries. We have lowered also the level of ambition for the management choices that could be introduced for the scenarios. So where we see that the first scenario, basically for both scenarios, we have defined the same management choices. That's first of all, lowering the organic content by lowering the food waste component. And we have lowered that as soon already introduced 20% for Asia. We did do that by 10% for Africa, just not to be over ambitious in the expectations that can be realized over there. And a second management choice we've been looking at is energy production from landfill gas. And then we mainly looked at the early introduction of landfill gas extraction and the effects of it on the total emissions of landfill gas. So I'll briefly take you through the dashboard sheets for each of these analyzed scenarios. That's 3 per scenario. And I then show you the results of our analysis. So the dashboard of the baseline scenario for the Northern African tropical dry scenario is this one. We have the usual moderate big landfill with 500,000 tons per year input, a 40 years lifetime, because that's what we see as a most realistic scenario for Africa, for the main city landfills over there. And the waste composition that's based on 50% food waste, 30% green and bulky waste, and 20% industrial waste. Most of the other scenarios in the other continents are using an MCF factor of 1.0 for well-managed and anaerobic landfills. But since the landfill management in Africa is lacking behind in most of the cases, for our scenarios, we've taken the MCF down to 0.8 unmanaged deep or high water table landfills. And consequently, we calculated the parameters that are connected those two scenarios. And of course, in most of the cases, there are small-scale landfill gas projects here and there scattered over the continent. But if you look to the main line, then there is no mean of gas control present yet. So that's why we have no any measures included in the baseline. Well, then by lowering the food waste component by 10%, we have recalculated the values for the operational aspects and recalculated the parameters. And made the scenario calculation with that, and the graphs of the results I will show you later on. And the same goes for the introduction of landfill gas extraction and energy recovery. Here, we did not, multiply the effects. So we did just measure by measure. So management choice is or DOC reduction, and this now is or energy recovery. So here the waste composition and amounts stay the same. The only thing we did here was recalculating the parameters based on the fact that landfill gas was assumed to be extracted during operation already with a low conservative amount of 30% recovery rate, and then a continuing of landfill gas extraction of 60% recovery rate after the finalization of the landfill operations. These are both conservative parameters, again, just to be realistic and not over-enthusiastic on the results that could be reached with this type of management choices. So we can go quickly through the other slides, because this is basically the same, only then for the wet scenario, the tropical wet baseline scenario. The main difference here is the parameters, where the DOCF and the reaction rate constant K are much higher. There's a larger part of the DOC turning into landfill gas, and it goes at a quicker rate due to the better conditions, climatological conditions for biodegradation. The other parameters are the same. And again, we did for lowering the food waste component by 10% an analysis, and consequently, we did that for the introduction of energy recovery as well, with the same parameters for 30% landfill gas recovery during operations and 60% after operations. Now, that results in the following graphs. Contrary to the other speakers of the other continents, you see much more smooth graphs here, and that's due to the fact that we did not calculate cell sizes. We took the landfill as a whole, because that's in fact that's the practice in Africa, and there are not really well organized landfill cells or spatial development of the landfill itself. So we see it as one big landfill body, and therefore we made the scenario. So no, tooth-shaped sawtooth graphs, but more smooth graphs due to the fact that we see it as one big landfill body. Well, the baseline scenario is the blue line, and the 10% reduction of the food waste results in a slight reduction of the landfill gas emissions, as you can see, that's the orange line. And by far the biggest effect can be reached even with conservative values for landfill gas extraction if we introduce early extraction and landfill gas utilization by energy recovery. That's the gray line, which is the most low, showing the most low emissions. Now, the graphs for the tropical wet scenarios look slightly different, and that's due to the fact that those reaction constants are much higher, and therefore the biodegradation goes much quicker. So you see a steep start of the curves getting to a stable high level because of the quick degradation. You get a quick production of landfill gas, but also if the waste is out of gas, all the organics are utilized, then it also drops down very quick after stopping the landfilling. That's the steep curve that you see after the stopping of the landfill. What is the same with the first scenario is that the limiting of 10% DOC is leading to a slight reduction of landfill gas emissions, and the introduction of landfill gas extraction is considerably much more useful in terms of reducing landfill gas emissions. So if I go to the last sheet for the African scenarios, then what we see is that by the reduction of DOC, you can, by 10%, you can reach a landfill gas emission reduction over the total lifespan of a landfill, and we calculated that over 100 years lifespan. You get a reduction of 5% compared to the baseline scenario. Looking at early introduction of energy recovery and continuing that after the end of the landfill operations, you can get results, emission reductions up to 32 to 40%, meaning that that's much more, in terms of reducing landfill gas emissions, it is more useful to look at management choices on the spot rather than to lower the DOC, for example, by limited percentages. So those are the first findings that we had in the African scenarios. I'll be happy now to pass on the floor to the South American scenario presenter, Mr. Thiago. Mr. Thiago has over 13 years been involved in landfill and waste treatment site selection studies and all kinds of works in South America, Argentina, Bolivia, Brazil, Peru, and so on. Thiago is also a board member of ABLP, and he will show you more about the things going on in South America. Thiago, please go ahead.
Thank you, Dennis. Hi, everyone. Let's talk about South America. Talk about the final disposal reality. We can see that we have about 27% of the municipal solid waste disposed in dump sites, but more than half of the waste is disposed in landfills. Due to the existence of dump sites and about our economical reality, there will be, we think that we expect in short and medium and also probably long term, the disposal of municipal solid waste is still, the landfill will be the main solution. So as I said, due to the existence of dump sites, it's expected the focus and priority, the regional priority will be the closure of dump sites and the construction mainly for new landfills. About the waste disposed here in South America, the main fraction is organic. And due of this, our landfills generate a lot of biogas and methane. And talk about the perspectives, the local, regional, and national governments, they have many initiatives and targets to reduce the amount of waste, organic waste disposed in landfill. But there are big limitations, many to economical and financial issues. So we think the trend is that the landfill, the waste disposed in the landfill, continue to be predominantly organic. Talking about the gas control in landfills in South America, in all countries, the 13 countries formed in South America, there is no mandatory gas control except in one state of Brazil, in São Paulo state. So the enforced gas for recovering the methane, it's common in big landfills, mainly in Brazil. Enclosed flares are still used here for generate carbon credits, but it's not a tendency here because the price of carbon credits nowadays. So in these big landfills, we use biogas thermal plants to generate energy, and also biomethane from LFG facilities are still increasing numbers, mainly here in Brazil. So, consider this reality I presented to this point. We choose 6 scenarios for South America, 3 of them for tropical wet climates, and the other for tropical dry climates. For all of we started here with talking about these scenarios. The criteria for all of them, we consider the gas recovery for all of them, and the criteria for end the activity gas recovery was the flow about 500 cubic meters of LFT gas per hour. We consider as I said, the energy use of biogas to generate electricity. And in all of them, we consider the early extraction starting 2 years in year 2 of each cell. We consider cells with lifespan of 2 years. So we consider the extraction in the second year of the operation of each cell. So for this, let's talk about the scenario. This first scenario considers 500,000 tons per year, operation period of 13 years. In all scenarios, consider this operational period. And waste composition, it's basically municipal solid waste, and the main composition is about a half food and waste and green waste. I didn't put here the other extraction, but there is still, it's important, the paper and wood in the waste composition. The first scenario consider tropical wet climate. In all scenarios, you consider well-managed anaerobic situation. This is the parameters in the gas control was controlled cell by cell. Talk about the second scenario. It's the same of the first scenario. We just consider a surface sealing. The surface sealing is implemented in each cell after about 3 years of closure of each cell, and we consider this surface sealing a use of geomembrane, which is being increasingly common here in South America, mainly in Brazil, in very rainy places. In the third scenario, it's the same it's kind of similar to the first scenario. What we changed is the amount of organic waste disposed in the landfill. So we reduced in the first scenario, we consider 500,000 tons per year disposed in the landfill. In this scenario, we reduced it to 375,000 tons per year, just reducing the organic matter in the waste fraction. For the fourth and 5 and 6 scenarios, we changed the climate option. the type. Now is tropical dry, and we consider the same parameters as the first scenario, considering the baseline operation. The fifth scenario includes the surface sealing, less the second scenario, and sorry, it's incorrect in the type of the presentation. The sixth scenarios consider the reduction of organic matter disposed in the landfill. So, consider all these 6 scenarios. These are the results, the curves. You can see in the top of the graphic the 3 top curves are about the tropical wet scenarios, and you can see. Let's move to the next. We can see that the 3 top curves. We can compare the baseline scenarios, the first and fourth scenario. When we use a surface seeding in the landfill, it provides a 21% methane emission reduction compared in scenario 2, and 49% reduction in scenario 5. Reducing the DOC input from 5% of municipal solid waste to 4% provides a 10% methane emission reduction for scenario 3 and 9% for scenario 6. And you can see that you can achieve a percent reduction in the level which you use a surface sealing. A greater reduction in the organic fraction exposed in the landfill is necessary. And you can see the energy recovery reduce the overall GHG impact of the landfill in all scenarios, and the maximum value reached was in the scenario 5, about 6.35% of the reduction of emissions. It's this. Now I introduce Mr. Bob Dick. Bob is Senior Vice President of SCS Engineers with over 30 years of experience to work on civil and environmental engineering projects related to solid waste management. He has performed landfill and landfill gas engineering projects, design, permitting, construction, and operations in more than 15 US states and several countries. Bobby?
Thank you, Tiago. Can you hear me okay?
Yes.
Okay. Well, hello, everybody. I'm honored and delighted to be able to present with my esteemed colleagues here on the management choices that were evaluated by doing this scenario modeling exercise on landfill methane emissions. And for North America, it's definitely challenging because of the wide variety that we have in terms of disposal facilities and their characteristics, and specifically the best management practices. So I thought I would take a minute in the introduction here before I get to the modeling, just to review the current situation and circumstances on North American landfills. And when you consider Canada, the United States of America, and Mexico, there is a wide variety and a diverse system of best management practices. And frankly, some facilities introduce these in a very progressive and aggressive manner, and some of them have little to no incorporation of these best management practices. So some of the industry best management practices that are common and typical in North America are the early and accelerated installation of a comprehensive landfill gas collection and control system. This obviously is the primary mitigation and abatement technology or strategy for reducing fugitive landfill gas emissions. And then the continued frequent expansion and even replacement of that gas system. Gas systems don't just live forever in an operating landfill. They're subjected to settlement and damage and filling operations. And so they need to be expanded into new cells and replaced when they become poor performing or marginal performance. And then I see frequently a combination of the vertical extraction wells as well as horizontal collectors and leachate cleanout connections to extract gas from the bottom of these engineered sanitary landfills from the leachate collection piping, which is a viable source of gas emissions. And then when it comes to other enhanced and progressive activities that are being done in our landfill gas collection systems, one thing we're finding is that the gas system can be, and the collection efficiency can be impeded or restricted by the presence of liquids, the leachate that accumulates in the waste mass, even at higher elevations. And so we're finding it's frequently necessary to have dedicated dewatering pumps positioned in the majority of the vertical wells. So we are dual extracting two fluids, the liquid, which is the leachate from the gas well, as well as the landfill gas itself. Another best management practice is to have multiple and redundant header pipe configurations so that if a portion of the collection network is dysfunctional or becomes impacted and is in need of repair, the gas can continue to flow in an alternate path, and multiple blowers. And we're even seeing the introduction of automated wellheads. So the use of artificial intelligence and programming with algorithms to continuously tune and balance the well field based on a certain predetermined set of criteria. And continuing on with the best management practices, we do have regulatory requirements to perform surface emissions monitoring, where we're actually evaluating and measuring methane right along the surface of the landfill in the US. Canada does not have that type of regulatory platform or program, and neither does Mexico at this time, but we're seeing more frequent use of manual and drone surface emissions monitorings to identify where fugitive landfill gas is being emitted, and that informs the design engineers, the landfill owner, and the construction crews of where to target additional controls. And then lastly, the use of geographic information systems based remote monitoring and control with technologies like a supervisory dashboard to be able to receive real-time data from your gas system and be able to react to that. So those are some of the best management practices. Again, not all are being implemented at each landfill related to landfill gas control systems. Now, some of the best management practices that aren't directly associated with landfill gas collection control systems that extract and recover the gas, but are indeed important to further restrict and impede fugitive gas emissions are your cover practices. And so excellent cover material practices on a daily basis, and then also limiting the working face dimensions. Obviously, we have to adhere to certain safety requirements to have adequate space for the collection vehicles to tip for the waste to be spread out in thin layers and compacted. But landfill operators can do certain techniques and strategies and implement protocols that limit the size of that working face, which is going to limit the area that gas can emit through areas that don't have good cover material. Also, we're seeing the introduction of bottom liner augmentation features when you construct a new cell at landfills in North America. Frequently, we're installing piping and aggregate stone in order to best extract gas immediately once waste is being placed and throughout the life and post-closure care period, and also to enhance liquids to move from the waste matrix at higher elevations down to the bottom where it can be collected and removed. You may have exposed geomembrane cap. That's becoming more common in North America in strategic areas. This is interim cover. It's not intended to last forever as a final cap. It's deployed to restrict fugitive emissions and then removed when filling comes back over that portion of the landfill waste footprint. And then certainly the aggressive and accelerated timing for placement of final cover systems is a best management practice. So with that introduction, when we considered North America landfill scenarios, we ultimately characterized essentially 3 different hypothetical landfills. And the first one in scenario 1, this is a high performing landfill in that it implements almost all of these industry best management practices in a very progressive and rigorous manner. And so when we looked at what scenarios to consider for a landfill that already behaves in a good manner to minimize fugitive landfill gas emissions, the 2 scenarios that were modeled was to lower the organic fraction, so a reduced degradable organic content is what we call North America Scenario 1A. North America Scenario 1B is the option to cap early in a cell-by-cell situation. And then we also modeled a scenario in which you would combine those 2 management strategies and do both. You would both reduce the DOC and cap in an early aggressive manner. And that was to assess a landfill that, again, in scenario 1, implements nearly all of these best management practices. In scenario 2, this is a landfill that isn't quite as rigorous in implementing these industry best management practices, although it does conform to regulatory requirements, but perhaps it's implementing these in a more limited or casual manner. And so that's the baseline for scenario 2. And then the management options we considered was 2A, earlier landfill gas extraction, and scenario 2B is to extend the period of landfill gas extraction. In other words, to not decommission the landfill gas in accordance with what's allowed by regulation, but to actually keep it operating longer into the post-closure period of the landfill. And the last hypothetical landfill we considered in scenario 3 is one that implements little to no industry best management practices. And these are around still in North America, landfills that really are not exercising these protocols as far as gas collection systems, cover practices, things like that. And so we looked at scenario 3A to reduce the cell size and scenario 3B to install a gas extraction system earlier than would typically be done on that type of a facility. And then, of course, in all 3 scenarios, there's a fourth modeling exercise, which is to have both 3A and 3B. Anyways, let's get to looking at what this really means as far as the input parameters. In scenario 1, which again, I remind you is all best management practices are being implemented, we looked at a temperate climate type, and the gas control is happening during operation. So this is when landfill gas systems are going in while the facility is continuing to place the waste in lifts. And again, scenario 1A was to lower the organic DOC fraction, and scenario 1B was for earlier capping. And I provide here the parameters of the reaction rate in the modeling. Now, what happens for scenario 1A, which is when you reduce the lower organic, you reduce the actual waste acceptance rates, you have a different waste composition, and so that changes your reaction rate. And this is just what I wanted you to focus on by looking at this, is the comparison of what input parameters actually change. So you see here in the green color, the input parameters for degradable organic carbon, and also the reaction rate for producing and generating landfill gas. And of course, when we have that on the left in the baseline scenario, and then in scenarios 1A, as well as scenarios 1A and 1B, that green shows you where the team changed the input parameters for organic content. And then the earlier capping, which is being evaluated in scenario 1B, what that really affects is the gas system collection efficiency can be introduced at a higher collection efficiency in an earlier time. And that does make a noticeable impact. And so the results of that are shown on this model, where you see a baseline in the orange-red color. And you notice that the scenario 1A, which is to reduce the degradable organic content, is shown in 1B. And that has a noticeable and substantial reduction from the baseline scenario. And remember, this is at a landfill that is already introduced numerous best management practices. So that blue line shows you the substantial reduction that can be achieved. But also notice the gray line, which is early capping, which achieves very similar reduction in methane emissions without needing the policy changes that are necessary to actually divert organic waste to some other managed facility other than a landfill. And then obviously what we would expect is when you introduce both the earlier capping and the reduction of degradable organic content as shown in the yellow line, that clearly is the ideal situation for this type of a facility, because you get a noticeable and substantial reduction. Scenario 2 was evaluated earlier gas extraction, and as scenario 2A, and as scenario 2B, the idea of continuing the operation of the gas system well into the post-closure period, beyond which would be the minimum required by the regulatory agencies. And so pay attention again to the input parameters when you're talking about implementing a management technique of early recovery. Then that's going to allow you to increase your collection efficiency. Obviously, when you talk about extended recovery in yellow, that's keeping the gas system active beyond the threshold that's established by the regulations here in the United States and what is just typical industry practices in Canada and Mexico. The results here, I need to point out that it looks like there's only 2 lines, but there's actually 4 scenarios there. It's just they're coinciding graphs. So the baseline of orange is actually hidden under the gray line with extended recovery, because the extended recovery scenario of 2B doesn't have any change to the modeling results until the very middle of the graph, where you see a distinction there between the differences. And then the early recovery, which is a blue line, is actually again hidden behind the yellow line, which is the both scenario. And so what we find on a landfill like this is that there is, achievable methane emission reductions that are beneficial to a facility for implementing early recovery, but the extended recovery does not seem to have that much impact, even on a landfill here with a temperate reaction rate, because most of the gas production and generation has already occurred by the time you get that far out into the life. The last landfill we looked at was one that had little to no best management practices. And like I said, these do exist. And so the management techniques that were most applicable for these type of facilities are scenario 3A, to reduce the cell size so that you're able to either cap or increase the collection efficiency on a higher frequency. And then scenario 3B, earlier landfill gas extraction, which is clearly one of the primary tools we have to reduce methane emissions. And so moving to the results here, what you see is this hypothetical landfill that doesn't introduce many of the best management practices. The orange line is the baseline, and you can achieve substantial reduction at certain periods in the life of this facility by implementing cell size reduction, because that allows you to install the gas system in that cell well in advance of the baseline scenario. And then the earlier recovery, the gray line, certainly is useful in reducing methane emissions, and the most ideal situation would be to implement both of those management practices as evidenced in the gray line. Now here, the yellow I point out, because we used a dry climate and the reaction rate was lower, when the landfill gas collection system is decommissioned after about 50 years, there's still a noticeable quantity of gas being generated. And so in a dry climate, it may be more beneficial to have that extended recovery as a management technique, whereas in my scenario 2, it didn't produce a substantial impact. And so the results for these 12 different scenarios are presented here. I draw your attention to the middle of the chart, where you see a row called percent of emissions. And that's really one of the things that I noticed told the story, the best story. For each of these scenarios, you can see the baseline and then see the percent of emissions compared to generation. And so we know that these management techniques and management options have a dramatic impact on reducing the fugitive methane emissions and being beneficial for air quality purposes. Thank you very much. With that, I'll pass it over to Hayo Sharaf. He's already been introduced to you, and Hayo was very instrumental and really demonstrated a lot of leadership during this, and I'm very appreciative to him. And you all already heard all of his credentials, so I'll just turn it over to you, Hayo. Thank you.
Thank you very much, Bob. I will now talk about Europe and the landfill trend in Europe is towards predominantly inorganic waste landfills with recycling activities on the landfills. The European legislation also wants more recycling and recovery, not only for municipal solid waste, but also for packaging waste, construction and demolition waste, and even for contaminated soils. The EU Landfill Directive has biodegradable municipal solid waste reduction targets. The target that should already have been reached in 2014 is therefore the baseline scenario for Europe. That means that less than 35% of the amount of municipal solid waste that was landfilled in the baseline year 1995 is still allowed in landfills. For the landfill that we are looking at, it was assumed that in 1995 it landfilled 100% municipal solid waste. So that is the worst case situation. The recent landfill directive states that by the year 2035, less than 10% of biodegradable municipal solid waste is allowed into landfills. And that is therefore, since it is already the law, that is therefore management option 1. We are assuming, since sanitary landfills are mandatory since 1999, that all landfills within Europe are already well-managed anaerobic landfills, so with a methane correction factor of 1. As I mentioned, we will use 400,000 tons of input per year over a period of 30 years, and in the baseline, that amount contained 35% biodegradable municipal solid waste. All of Europe is within the temperate and boreal dry climate zone, according to the IPCC definitions. So we did not have to make a distinction there, other than that there might be a reaction rate difference for the wet and the dry areas. I have stated here that the gas control that was assumed in the baseline is control after landfill operation, gas control after landfill operation. So that starts in the year 32. The reduced DOC scenario, that is option 1, since that is already the legislation. In the baseline, 35% of the 500,000 tons, so that is 175,000 tons, was municipal solid waste. If you go down to 10%, that is only 50,000 tons. So you have to reduce by 125,000 tons. And therefore, the input has been lowered to 35,000 tons. That means that actually, since the amount goes down, the percentage in the waste composition is a little bit higher, but the percentages for C&D and for industrial waste, they actually go up. That results in a couple of changes, not too dramatic, but nevertheless changes in degradable organic carbon content, the fraction that actually degrades, and the reaction rate constant. Still, control after landfill operation. Now, you may wonder why that is. The text on this slide is all the text that there is on landfill gas control in the European Landfill Directive. The reference to Annex 3 in this Article 4.1 is meaningless because it is not about measures, but about monitoring. So what is mostly failing here is the moment when you have to put in your gas control. And that leads to the fact that in many EU member states, it is still common practice that gas wells are installed only after the entire landfill has reached its final height. That is the reason that that is in the baseline scenario. Even though gas control is mandatory in entire area of Europe, all the European member states since 2001, that is 2 years after the implementation of the Landfill Directive. The problem here is that the wording is vague, and in many member states, the enforcement is very weak. So therefore, option 2 is gas control on a cell-by-cell basis. That can either be done in the schematics and in the pictures here by installing vertical gas wells, or it can be done, as was shown by previous speakers, by installing horizontal gas wells. Only a very few member states actually enforce gas recovery during waste placement. I know it from Ireland and I know it from the UK, but they have actually left Europe. That is therefore option 3. And then there's a new development, especially Germany is very active in this field, and that is over-extraction. So you actually extract a higher volume of gas than is generated, which means that you are taking in atmospheric air. By doing that, you reduce the fugitive emissions, but you end up with a gas quality that is no longer suitable for energy recovery in a gas engine, and you have to flare it in a low calorific flare. There are flares on the market nowadays that still burn with methane percentages as low as 5%. So, quickly through the dashboards, superimposed on the degradable organic carbon reduction, because that is already the law, is control, gas control of cell by cell. And then in the next option, option number 3, one step further, gas control during cell operation. And then finally, over extraction and low calorific flaring. That has generated 4 graphs. And in this slide, you also see 2 other graphs, an orange one and one that is actually not indicated because it is covered by the orange one, that's a blue one. These are 2 scenarios for Europe with a wet climate, so that has slightly higher degradation rates, reaction rate constants, meaning that the gas is produced more quickly in the beginning, and therefore there is less left in the end. I initially used this scenario to demonstrate the impact. That already was a question in the questions chat. What is the impact of improved oxidation in top covers? Now, in the case of Europe, and so that is not a typical situation. You are only, in many member states, you are allowed to do that when you are no longer able to actively extract the gas. In Germany and in some other member states, for instance, you can only do that when the gas generation has dropped below 50 cubic meters per hour. That is actually happening at the very far end of landfill life. This line here is, of course, it's difficult because this is expressed in megagrams methane, but it is somewhere 10 or 12 years before the 100-year period is over. So you can imagine that improving the oxidation rate from 10% to 50% at that moment hardly impacts the overall greenhouse gas emission of the landfill. So since in a dry climate the reaction rate constant is lower, more gas is produced in later years. And therefore, we focused the other options on the later years. So what you see is the yellow, the gray line is the baseline for the dry areas in Europe, and the yellow line indicates the impact of the reduced organics according to the current legislation in Europe. Superimposed on that, you can start earlier extraction. That is that is EU2D. That gives you an improvement, and you can get further improvement if you do early recovery. So you already start extracting during filling of the cell. And finally, you can even get more reduction if you extract by means of over-extraction and do low calorific flaring. In specific situations, you can get an additional reduction if you use the gas for energy recovery. But energy recovery in the European scenarios only reduces the overall greenhouse gas impact by 3 to 4% of the methane generated in that scenario. So there is not a lot of environmental benefit there, and it is actually a lot better, or a lot is maybe a bit exaggerated, but you can get a better performance if you stop the energy recovery and move over to low calorific flaring. Most important for the European scenarios is that reducing the organic waste input according to legislation that is already in place reduces by 40%. If you start gas recovery on a cell-by-cell basis, then you increase up to 57% reduction compared to the baseline scenario. If you realize gas recovery during filling, then you can get up to 60% emission reduction. And if you perform low calorific flaring and over extraction, it increases to 80% of the baseline scenario. That brings me to the overall conclusions and observations of all the modeling efforts that were performed all over the continents. And if you look at those scenarios, essentially there are two options that are the most important for methane emission reduction. Some of the speakers have already mentioned it. Early gas recovery is actually the most important one. The earlier you start, the lower your overall methane emission during the landfill life is. Reduction of degradable organic carbon input is also an important one, but only if it is not limited to food waste, if it is a serious reduction, and if it also includes yard waste and especially paper and cardboard. Early construction of a surface sealing, as we have seen, increases the recovery efficiency, but it may come at a price because some regulators do not accept that early installed surface sealing as the final surface sealing when you want to hand over and stop aftercare, for instance. So it could be an expensive option. Improvement of passive oxidation. At the moment that active recovery becomes difficult, has a very low impact on the overall methane emission, but that is when you impose it, when you apply it in situations at the very, very end, when active extraction has become technically impossible. There was a question in the chat, what if you use methane oxidation covers on landfills that produce a lot of methane? The problem there is that the capacity of methane oxidation covers is limited. So in those cases, you would probably need a surface area that is orders of magnitude higher than the actual surface of the landfill to passively oxidize all the methane that is produced in that landfill. What we also saw that the additional benefit of energy recovery, and that is then in terms of avoided fuel, strongly depends on the energy mix in the country at hand. For instance, if you would do it in Sweden, Sweden relies to a very large extent on hydropower and to a certain extent on nuclear power, but both are considered not to have greenhouse gas emissions. And therefore, in Sweden, there is very little to avoid. And that, for instance, also applies to New Zealand. But even if you apply it in countries that still rely to a large extent on coal-fired power production, it never exceeds 10% of the methane generated. And it will decline with progress towards a more sustainable energy mix. And as the European scenarios indicated, higher reduction seems possible without energy recovery. Unless, of course, you install a surface sealing very early and consider it as a temporary sacrificial surface sealing. And then you can extract with high efficiency rates a gas quality that is suited for energy recovery. So I think that ends the inputs that we would like to share with you today, and we can move over to the questions and the discussion.
Thank you, Hale. And I would like to invite our presenters to either unmute yourself or you can turn on your video if you wish, so that we can all participate in the Q&A sections. There is one question for Sun. It is about whether the Asian scenario is an example of waste composition from Malaysia, and if it is not, what is the basis of the choosing the waste composition for Asia? I guess the point here is the waste composition vary quite a bit, and you know, whether one scenario can represent everything. So maybe you can try to respond, and then you know, the rest of the speaker can chime in if you wish, because based on your modeling experience, that maybe information will be all useful to share. Sun on the line? No?
I think we have lost Sun.
Yeah.
I can try to give an answer in his place.
Sure.
I also saw the question in the Q&A tab.
Mm-hmm.
Yes, the Asian scenario is derived from Malaysia. And yes, probably the food waste composition does change a bit in different countries in Asia. Also across Asia, there are differences in climate, but we have chosen to illustrate. And we think that if you start modeling with a slightly different food waste composition, you will still find the same trend. So therefore, we have decided not to do any imaginable scenario that would increase the calculation work too much. But if there are reasons to assume that there is a situation within Asia that is hugely different, then we could certainly consider to look at that. There was a question added to all this, and that is, did you include uncertainties in the calculation? No, we didn't. And that again increases the work tremendously. We wanted to illustrate, we wanted to show trends. And if we start applying uncertainties, the thing to do would be to apply the uncertainties as are described in documents that are produced by IPCC. But they then would be the same throughout all the scenarios. So it would not give us a lot of benefit where we compare the different scenarios. It would not change the conclusions. So I hope that answers the question.
James, I think you're on mute.
Sorry. Sorry about that. Common mistake. So there was a question about the Asian scenario presented, whether it is the waste composition from Malaysia, and if you consider other Asian countries, I think the question is from Vietnam, and then if you consider their waste composition, whether the result would change much.
Yeah, sorry, I got disconnected for some reason. I don't know why. Yeah, the composition that we used for the modeling was based on Malaysian waste composition, but I had been looking at different types of waste composition in Asia, and they are pretty similar. So I think including in Vietnam, you will still also have very high percentage of food waste. Just like Malaysia. So I will imagine the results will be pretty similar in this case.
Okay. Oops. Max, can you bring us back to the presenter screen? Okay, is there any other question that we noticed there?
Yeah, there are two more questions, James.
Oh, okay.
The first one was that it was observed that early gas recovery seems to provide important benefits in terms of greenhouse gas reductions, but that this can be very challenging in developing countries, where many sites are not properly designed and they do not operate as sanitary landfills. Mm-hmm. And the question is it feasible to have an effective gas extraction in such cases? I can try to give an answer, but maybe some of the other speakers would also comment on that. Yes, it may be a challenge to actually do that in developing countries, but our work is mainly focused at pointing out what kind of a reduction could be achieved. And whether that actually is achieved, that is a different question. We will consider if we can do a follow-up project with the outcome of this work, especially since UNEP has recently also written a report where they basically come to the same conclusion that in reducing methane emissions from landfills, there is a very good opportunity to actually reduce the radiative forcing very quickly. But that would mean that means have to be made available in order to do that. That is a political, that requires political lobby work. I'm not sure how far we can go, but we will definitely consider it.
Yeah, just probably like to add, Joe, that if it's a poorly run landfill without compaction, where the waste is likely being burnt, that the amount of organics left to turn into gas are probably going to be fairly low to start with. So the overall methane impact of that's probably going to be on the lower end anyway.
Mm-hmm. And I guess we can move on to the next question. What is the recommended frequency of surface emission monitoring? And second part of the question is drone technologies mature enough to do such a task of monitoring? This may be a question for Bob, I think.
Yeah, James, thanks. I think right now in the US, the frequency of surface emissions monitoring is required to be quarterly, so 4 times a year. So about once every 3 months, you are required to conduct surface emissions monitoring on a 30-meter serpentine grid pattern, as well as at all of your pipe penetrations of the cover system. And so that's certainly the required. Now the question is, what is recommended frequency? I will say that I'm aware of numerous landfills that whether for odor control purposes or for other reasons for design purposes, actually conduct surface emissions monitoring on about a monthly basis. And then the second part of the question, drone technology. So what happens is you affix a tunable diode laser to the drone that is, calibrated to measure methane concentrations. We don't have that as a approved method for regulatory compliance yet, but the results I've seen of where it's been implemented are valid. They appear to be valid. They appear to be a reliable strategy, even if the actual numerical values are perhaps can't be confirmed or validated. It's a relative, it's useful as a relative tool to tell where you have more emissions. And it is rather specific, the number of, pixelated points that comes in the output of that. So I believe it's a robust and useful technology. I don't know exactly what ripe enough means, but I'm assuming that it's gaining in credibility and reliability and acceptance. Thank you.
Very good. Any other observation in other continents regarding this question? Let's move to the next question. What about bioreactor landfill approach with landfill gas collections to reduce landfill gas emissions?
Can I take that one, James?
Yep, sure. Hey, go ahead.
Because I already answered the question in writing in the questions section. About the impact of landfill recirculation. So that is basically in the same area.
Mm-hmm.
Bioreactor landfills attempt to do several things. To do, by means of leachate recirculation, increase the reaction rate constant. And they also attempt to recover a higher amount of gas by installing gas collection early and by capping early. And basically, that is factors that we, without calling it a bioreactor landfill, have looked at during our modeling exercises. What we did not include is increase the reaction rate constant. And the problem here is that there is a lot of information out there about increasing reaction rate constants in lysimeters or landfill simulation reactors. But there is very little reliable data on how these measures can increase a reaction rate constant in an actual bioreactor landfill. So this is hard to model. If you have these reaction rate constants, then you could do it. But what it boils down to, we have looked at improved landfill gas collection, and we have looked at early installing of surface sealings, and that is what a landfill bioreactor also does.
Very good. Okay, I think that's all the questions that we have. And first of all, I'd like to thanks everybody for participating in today's webinar, and particularly to our presenters and Jonathan, as Jonathan way past his bedtime and soon going to be. So I appreciate your participation and hang out there for us. And particularly, I'd like to thank the employers of our speakers today for allowing them to volunteers their time to make this webinar and studies analysis possible. And I look forward to the teams putting together the white papers possibly toward the end of the year. And the work is still continue after this webinar. And I'd like to congratulate all of them for their endurance and their willingness to give us this wonderful presentations. And if you have any other questions regarding this, you can always email to the General Secretary of ISWA, and then we'll try to incorporate that in our final products coming soon. And the recorded version will be posted. The link will be sent to you, and so as the PowerPoint in PDF format. So thank you again for everybody participation, and looking forward to see you guys again in another platform. Thank you.